All right, so after introducing Einstein's E equals mc squared formula, finally in physics, you got to be able to use this formula. What we got to remember is that it helps us calculate the binding energy of the nucleus, which is the work required to separate the nucleons of a nucleus. All right, it gives us an idea about the strong force. A reminder that m is the mass defect, which I showed in the past video. When you add up the free protons and free neutrons and put them into the nucleus, and you add the mass of those free protons and free neutrons, it doesn't add up to the mass of the actual nucleus. There's a defect. And if I take that mass defect, that difference, and I multiply it by the speed of light squared, that gives me the binding energy according to Einstein. So we're going to go through a few sample calculations to show you how you're going to calculate the binding energy of different nuclei. All right? Important to memorize this definition. It often appears on exams, so quick and easy thing to be able to get a couple marks. All right, so what you got to remember is that the binding energy is directly proportional to the mass defect. The larger the defect, the more binding energy is involved in that nucleus. So problem one that I want to go over is finding the mass defect of a nucleus of gold. Gold has a nucleon number of 197 and a proton number of 79. And if I just look at the mass of the nucleus, I weigh it, doing the same procedures we did in the past videos, the nuclear mass is 196.924 atomic mass units, U. Okay, so how do I use that number and the numbers here to find the mass defect? Okay, and here's how you're going to do it. The first step that you have to do is you have to find the number of protons, 79, and the number of neutrons. I subtract that number from that number to get the number of neutrons. Now that I have that, I can find out what the theoretical mass of the free protons and the free neutrons would be. So the mass defect is going to be your actual mass minus the mass of the free protons plus the mass of the free neutrons. Okay, so how do I find the mass of the free protons? In your data booklet, it'll tell you how many atomic mass units a free proton is and how many atomic mass units a free neutron is. And here it is. A free proton has that mass. Okay, it's a little larger than the individual, the 1/12 of carbon, like I talked about in the previous video. It's 1.007276. And the mass of a free neutron is 1.008665 U. You see it's a little larger because they're free. Okay, when you multiply that together and subtract, you get this number. You can try that. Okay, so the mass defect inside of gold is actually a whole mass defect, a whole mass unit. So it's negative 1.67. You just think about the absolute number of that. So the mass defect is 1.67 atomic mass units. So then how would I use that to find the energy? Well, the binding energy, okay, that mass is not lost. It's converted into binding energy. So that binding energy, I plug it into this formula, E equals mc squared. Okay, and then here's my mass defect, M, 1.67 U, times the mass in kilograms. Remember, mass in a formula is in kilograms, so I got to convert U into kilograms, and that is the mass of an atomic mass unit, 1/12 the mass of carbon. So when I multiply that, I convert that into kilograms. Multiplied by the speed of light squared will give me my binding energy, which it seems like it's really, really small, but that's just for one nucleus, okay? Now, remember, in atomic physics, we don't like to use these, exponents down there. So we found a new unit of energy called electron volts. So I can convert this into electron volts by dividing by 1.6 times 10 to the negative 19 joules per electron volt. And then that gives me a value of 1.56 times 10 to the 9 electron volts, or 1,560 mega electron volts. So you'll see this often as units in the problems in your textbook. Okay, calculate the electron volts of binding energy. Okay, so that's a lot. That seems like it's a lot of electron volts for the binding energy of the nucleus. But wow, what a lengthy process this was. A very lengthy process. But I'm going to show you a quick trick. Okay, so there's a fast trick that you can do. Rather than plugging it into equals mc squared, if I plugged in one atomic mass unit into E equals mc squared, I'm going to find out that the binding energy of one atomic mass unit is 931.5 mega electron volts. So I can use that as a ratio. So instead of always plugging it into E equals mc squared, I can take a look at my mass defect for gold, which was 1.67. And if I multiply by 931.5, it'll give me the same answer. Okay, because all I'm doing is the energy associated with one mass unit making a ratio and just multiplying by whatever mass units I have in my mass defect. And then I'm able to calculate. So it's a quick trick that students often like to use on exams rather than always plugging it into this formula. Okay, because if you plugged it in this formula, you have to convert to kilograms, and then you got to use a bunch of scientific notation. It just takes a long time. So that's a quick trick. Again, the fast trick. So try to make a note of this and try to do some practice problems with this just to make sure that you know how to use it well. And then you can really save a good 5 minutes on the exam using that fast trick.